What is the highest temperature in the universe? In fact, the essence of temperature is the wild dancing of atoms and molecules in the microscopic world. The more violently particles move, the faster they go, and the higher the temperature becomes. Take the ordinary 27 degrees Celsius air around us. Oxygen molecules inside it move at an average speed of about 1,800 kilometers per hour, more than twice as fast as a commercial jet. The only reason you don't feel a raging wind is that these tiny particles are moving randomly in all directions, not in a single, unified flow. If you could completely stop all particle motion, you would reach the lower limit of temperature, absolute zero, at minus 273.15 degrees Celsius. So here's the question. If cold has a limit, can heat increase infinitely? Let's start from the temperatures we're familiar with and climb upwards step by step to see just how extreme heat can get. The temperature at which butter melts is only about 1.5 degrees Celsius lower than normal human body temperature. But once it exceeds 42 degrees Celsius, a high fever can become deadly. This is the thermal limit the human body can endure. At 57 degrees Celsius, we reach the highest temperature ever recorded on Earth in shaded, well-ventilated conditions without direct sunlight. Simply standing there, the air you breathe feels scorching. Beyond the limits of life, heat begins to affect ordinary matter. At 100 degrees Celsius, water boils under normal atmospheric pressure, forming bubbles that carry heat away. Above 121 degrees Celsius, even the most heat-resistant extremophile bacteria in deep-sea hydrothermal vents cannot survive. Around 125 degrees Celsius is the safety limit for computer processors. Most CPUs shut down around 100 degrees Celsius, while some specialized chips can reach about 125 degrees Celsius before automatically powering off to avoid damage. At 180 degrees Celsius, the water inside corn rapidly expands and bursts, turning into popcorn. These everyday thermal limits are insignificant compared to truly high temperatures. As we go higher, even metals begin to surrender. At 327 degrees Celsius, lead melts into a soft liquid. At 357 degrees Celsius, mercury boils and can no longer function in a thermometer. At 427 degrees Celsius, you get the surface temperature of Mercury, while Venus reaches about 462 degrees Celsius, the hottest planet in the solar system, hot enough to melt solder. At 525 degrees Celsius, something fascinating happens. You can finally see heat. Before this point, objects emit only infrared radiation, which is invisible to the human eye. You can feel the heat, but you can't see it. But beyond 525 degrees Celsius, metals glow red, stones begin to shine, heat becomes visible as light. As temperature rises, the color grows more intense, from dull red to bright red, then white hot, and eventually bluish. The brighter the glow, the more extreme the heat. At 962 degrees Celsius, silver melts into liquid. At 1200 degrees Celsius, volcanic lava flows, like the eruptions of Hawaii's Kilauea volcano, creating a hellish landscape where nothing survives. At 1400 degrees Celsius, even the small flame of a candle reaches its peak temperature. It's astonishing that such a tiny flame contains such immense heat. At 1538 degrees Celsius, iron melts into molten metal, the core temperature of steel furnaces. Go even higher, and pure carbon cannot hold on. Under high pressure, carbon melts at about 3,550 degrees Celsius and boils at around 4,027 degrees Celsius. At 5,660 degrees Celsius, all metals in the universe exist in gaseous form. Coincidentally, this is also the surface temperature of the Sun, the giant fireball that illuminates our solar system. But the Sun's surface is only an entry-level temperature in the world of stars. Even Earth's core reaches about 6,000 degrees Celsius, hotter than the Sun's surface. Across the universe, stars grow even hotter. Polaris has a surface temperature of about 6,600 degrees Celsius. Sirius, the brightest star in the night sky, reaches about 9,500 degrees Celsius. The core of the gas giant Jupiter reaches around 24,000 degrees Celsius, while some blue supergiant stars nearing supernova can have surface temperatures as high as 37,000 degrees Celsius. But no stellar surface compares to its core, the furnace of nuclear fusion. The Sun's core reaches about 15 million degrees Celsius, where hydrogen atoms fuse into helium, releasing the energy that lights up the solar system. In red giants, core temperatures can reach 200 million degrees Celsius, enabling the fusion of heavier elements like helium. In the final days of a supergiant star's life, Its core temperature can soar to 2.5 billion degrees Celsius. This is the ultimate limit for stars. Beyond this comes the catastrophic explosion of a supernova, scattering its material into space. What remains afterward can be even hotter, a neutron star. Inside a neutron star, temperatures reach up to 120 billion degrees Celsius, the upper limit for stable massive objects in the universe. A single spoonful of neutron star material would weigh as much as a mountain, yet still radiate unimaginable heat. But is this the end of extreme temperatures? Not even close. In the centers of quasars, supermassive black holes devour surrounding matter. As this matter is torn apart and accelerated, it can be heated to around 10 trillion degrees Celsius, nearly 1,000 times hotter than a neutron star. At around 1.7 trillion degrees Celsius, a critical threshold appears, the temperature of quark deconfinement. Beyond this point, protons and neutrons themselves break apart into quarks and gluons, forming a quark-gluon plasma, a shapeless, ultra-hot soup of fundamental particles. This represents the highest temperature at which matter, as we understand it, can exist. Remarkably, humanity has recreated even higher temperatures on Earth. At the Large Hadron Collider, atomic nuclei are accelerated to near light speed and smashed together, briefly generating temperatures of about 5.5 trillion degrees Celsius. Though the state lasts only an instant and involves very few particles, it proves that humans can touch cosmic-level heat. Yet even this pales in comparison to the birth of the universe. About 13.7 billion years ago, at the moment of the Big Bang, temperatures reached approximately 1.4 times 10 to the 3rd degrees Celsius, the Planck temperature. The entire universe was an unimaginably hot particle soup, with space and time themselves still in a chaotic, undefined state. And this brings us to the ultimate limit. Physics itself draws a final boundary. The Planck temperature, about 1.417 times 10 to the 3rd degrees Celsius, the highest temperature our current theories can describe. Beyond this point, both quantum mechanics and general relativity break down. Particle energies exceed what current physics can explain. Light wavelengths become smaller than the smallest meaningful unit of space. Extreme energy compressed into infinitesimal space could form photon black holes. Even space-time itself loses its structure, becoming chaotic and undefined. At this boundary, all our physical equations collapse into meaninglessness. We cannot yet say what lies beyond the Planck temperature, not because higher temperatures cannot exist, but because our science has not yet reached that frontier. Perhaps beyond that blazing limit lies the ultimate secret of the universe's origin, hidden behind a veil we are only just beginning to glimpse.